Hello students, welcome back to the series Coordination Chemistry. In this module, we will be continuing the theories of coordination compounds, particularly John-Teller distortion. In the last class, we were discussing about different crystal field splitting in the different field, that is crystal field splitting in tetrahedral, square planar, tetragonal, etc. And in here we are discussing the tetragonal complexes or tetragonal distortion, that is John-Teller distortion in detail. And how we are arriving, how we are getting the tetragonal complexes. See, the octahedral complexes are perfectly symmetric or perfectly symmetric complexes, that is here you can see the perfect symmetry in the octahedral complexes. And from the octahedral complexes, when we are moving to the square planar complex, you will get the intermediate as the thing that is shown in the middle of the picture, that is we are just elongating the ligands along the z axis, that is elongation, z elongation, and in between the square planar and octahedral complex, you can see an intermediate, that these are called as tetragonal complexes, or any distortion from the octahedral complexes you will get a tetragonal complex. So, 100% distortion in octahedral complexes lead to a square planar complex, and intermediate of these two will get the tetragonal complexes. And this tetragonal complexes or tetragonal distortion can be also called as John-Teller distortion. And there is a theorem called John-Teller theorem. What is John-Teller theorem? Any nonlinear molecule in a degenerate electronic state will undergo certain kind of distortion to lower the symmetry, lower the energy to attain the stability. So, that is the John-Teller theorem. It is discussing, it is concerned with the degenerate electronic state. So, any nonlinear, the molecule which is a nonlinear one, when there is a degenerate electronic state, that will undergo some kind of distortion. Why it is undergoing distortion? To lower the symmetry, lower the energy, that is to attain the stability. That is all about the John-Teller theorem. And we have already discussed that the perfect octahedron, that is perfectly symmetric octahedron, when we are moving from a perfectly symmetric octahedron to a complete 100% distortion, that is a square planar complex, in between there is a tetragonal complex, and how the John-Teller distortion occurs is discussed here in detail. Since we have seen that two types of complexes are there, that is high spin complexes and low spin complexes. High spin complexes are having their spin maximum, that is electron will not be paired, or it will be occupying a higher energy state, that is the excess electron, or in the case of this octahedral complexes, the after third electron, the fourth will be moving to the EG orbital, that is, they are called as high spin complexes. Low spin complexes means they are having the spin paired, means we have maximum number of paired electrons in the case of low spin complexes. All those high spin and low spin complexes were discussed in detail in the previous classes. And when we consider different systems, that is D1 to D10, see in the first case, if we are considering a D1 system, means one electron in the d orbital, and that one electron in the octahedral field, if the field is an octahedral field, that one electron will be moving to the T2G orbital. You have three T2G orbitals, that is dxz, dyz and dxy, and that electron, one electron will be either moving either to these three orbitals. It may go to the dxz, dyz or dxy. So, there are three possibilities for that electron to move to these three orbitals. That is why there is a degeneracy in the case of D1 system, means that single electron may occupy either of these dxz, dyz or dxy orbital. It can occupy these three orbitals because these three orbitals are having a degenerate energy state. That is why there is a type of weak distortion in that complex. So, you can see what is John-Teller theorem, that is any nonlinear molecule in a degenerate electronic state will be having some kind of distortion, and non-degenerate means, see this degenerate means in the T2G orbital you have 3 degenerate orbital, and that single electron may occupy dxz, dyz or dxy. That is why a weak distortion is there in the case of D1 complex. And now moving to the D2 complex means 2 electrons are there in the T2G orbital. That 2 electrons may be, they have 2 electrons can occupy in different type, means 2 may be occupying dxz, dyz and dxy will be having a 0 electron, or there are some kind of combinations possible in the case of D2 system. That is why there is a weak distortion in the case of D2 system. Again, the molecule, if we are considering a nonlinear molecule in a degenerate electronic state will be undergoing some kind of distortion according to the John-Teller theorem. So, a weak John-Teller distortion is there in also there in the case of D2 state. And while considering the D3 state, D3 means 3 electron in the T2G orbital, means we have 3 d orbitals dxz, dyz and dxy, and 3 electrons will be occupied equally among these 3 orbitals. So, there are no degenerate, there is no unsymmetrical arrangement possible in the case of D3 system, because each T2G orbitals are singly occupied. So, there will be no distortion in the case of D3 system. But when we are considering this, we are discussing about the high spin complexes. If it is a D4 system, D4 high spin system, what is the case? See, high spin means after the 3 electron, after the occupancy of these 3 electron in the 3 T2G orbital, the 4th electron will be moving to the EG orbital. So, this is the situation T2G3 and EG1. That EG how many orbitals are there in the EG? We have 2 orbitals, that is dz square and dx square minus y square. That single electron may occupy either dx square minus y square or dz square. That is why there is a strong distortion there in the case of D4 high spin. D4 high spin state, you have a strong distortion, because there that 4th electron may occupy either dx square minus y square or dz square. While we are considering the D5 system, that is D5 high spin system, after the 3rd electron, 4th will be moving to the EG, 5th also will be there in the EG. So, the 5th electron, there is, for the occupancy of the 5th electron in the EG orbital, it has no it has no options. It may go to the after 4th it should go to the next EG orbital. So, that is why there is no distortion in the case of D5 system. That is, complete absence of John-Teller distortion is there in the D5 system. And now D6 high spin. D6 means after the T2G, after the occupancy, after the 3 T2G orbitals, 4th will be moving to the up, 5th will be there in the up, and the 6th should come to the T2G orbital. So, that 6th electron can occupy either of the we have 3 T2G orbitals, it can occupy in dxy, dxz or dyz. That is why it is having a weak distortion. So, when there is a choice for that electron to occupy the degenerate state, there will be a weak distortion. And when it is D7 high spin, D7 high spin also the situation is similar, because after the 1, 2, 3, 4, 5, after the 5th electron, 6th will be moving to the T2G, 7th will be also in the T2G. That 7th electron can go either dxz or dyz. If dxy is already been occupied by the 2 electron, it can occupy either of the 2. So, there is an option for that electron, that is why there is a weak distortion. And now moving to the D8 system. D8 means after this 1, 2, 3, 4, 5, 6, 7. After the 7th occupancy, 8th electron there is, for that 8th electron, it does not have any option of choosing. So, there cannot be any distortion because the 8th electron should occupy the T2G orbital only. There is no option for that 8th electron. That is why no distortion is there in the D8 high spin complex. And now moving to the D9 complex, the situation is very much different. D9 means after the 8th electron, after the complete occupancy of the T2G orbital, the 9th electron should go to the EG orbital. So, that 9th electron has an option. It can either occupy dx square minus y square or dz square. So, when such situation occurs, there will be a strong distortion in the case of D9 system, which is very important. And now moving to the D10 system, there is a complete symmetric arrangement, or 6 electrons in the T2G and 4 electrons in the EG orbital. So, complete absence of the distortion, that is no distortion in the case of D10 system high spin. And now we can consider the low spin complexes in detail, that is D1 means there is no difference between D1 high spin and D1 low spin, D2 high spin and D2 low spin, D3 high spin and D3 low spin. The situation is similar in these D1, D2, D3 cases in high spin and low spin complexes. And now we have to discuss D4 case. D4 means the 4th electron. In the case of low spin complexes, the 4th electron cannot move to the higher EG state. It should occupy in the lower T2G only. So, since the electron is occupying in the T2G orbital, that electron has an option to go to either of the it can occupy to dxy, dxz, dyz orbital. In any 3 it can occupy, that is why it is having a weak distortion, that is D4 low spin. Now moving to the D5 low spin means after the 4th electron, 5th also should be occupied in the T2G orbital, and also it is the 5th electron is also having an option of occupying, that is why it is having a weak distortion. Now moving to the D6 case, D6 low spin means after the 5th, 6th should be occupied only in the T2G only. So, the T2G orbitals are completely filled now in the case of D6 low spin complex, means all T2G orbitals are completely filled. That is why there is no distortion at all. There is no option for that 6th electron for the occupancy. And now D7 system, D7 low spin means, now coming to the D7, after the complete occupancy in the T2G orbital, the 7th electron should go to the EG orbital. EG is, we have 2 EG orbitals, dx square minus y square and dz square, and there is a option for that electron to move to either dx square minus y square or dz square. That is why a strong distortion or strong John-Teller distortion is seen in the case of D7 low spin. And D8, in the case of D8 means the 8th electron, there is no option for that electron to occupy the either of the EG orbital. So, the 8th electron should go to only one EG orbital, that is why no distortion in the case of D8 system. D9, the situation is different. D9 means after the symmetric arrangement of the EG orbital, the 9th one has 2 options, either it can occupy to dx square minus y square or dz square. That is why there is a strong distortion. And D10, obviously there will be no distortion. So, these are the cases of high spin and low spin complexes showing John-Teller distortion. And while we calculated, or while we look at the John-Teller distortion in different systems, we understood that high spin D4 high spin, low spin D7 and D9 systems, high spin D4, low spin D7 and D9 systems undergoes strong John-Teller distortion. See this, high spin D4, low spin D7 and D9, high spin D4, low spin D7 and D9. They are showing strong John-Teller distortion. What is the peculiarity of these complexes? See the case of D4 system. In the D4 system, the electron was occupying the EG orbital. that is D4 high spin. When we look at the D7 low spin, that electron is also occupying the Eg orbital, and D9 also is occupying the Eg orbital. So, we have to conclude that when there is a unsymmetrical arrangement, when there is a degenerate state in the case of an Eg orbital, when the electrons are have an option to occupy the Eg orbital, there will be a strong Jahn-Teller distortion. That is seen here. That is Eg orbitals with the unsymmetrical distribution, means if there is a single electron in Eg, means a single electron in Eg means there is an unsymmetrical electronic arrangement, because symmetrical means when we are saying about the when we are discussing about the symmetrical and unsymmetrical, Eg2 means it is a symmetrical arrangement, Eg4 means also it is a symmetrical arrangement. Eg1 is an unsymmetrical arrangement, Eg3 is an unsymmetrical arrangement. So, the Eg orbitals with the unsymmetrical distribution of electrons will give more distortion, since Eg orbitals are lying along the direction of the incoming ligands. We have already discussed in the previous classes that how the splitting of the d orbitals occurs in the octahedral field. Why the Eg orbitals are having a greater energy? Because the Eg orbitals are lying along the axis. Since there is a head-on interaction of these orbitals with the incoming ligands, the energy is being raised. And so, similar is the situation here also. If the Eg orbitals, since they are lying along the axis, when there is an unsymmetrical arrangement, they will be having a greater repulsion. That is why a strong Jahn-Teller distortion is seen in the case of unsymmetrical electronic arrangement in the case of Eg orbital, that is Eg1 or Eg3. See, Eg1 means this D4 is Eg1, D7 low spin is Eg1, D9 low spin is Eg3. If it is Eg1 or Eg3, there will be a complete Jahn-Teller distortion possible. And thus the D9 system contains 3 electrons, that is Eg3. It was Eg3 in the case of D9 system. So, thus the D9 system containing 3 electron in the Eg orbitals will have a more tetragonal distortion. That is very important. That is, it is particularly seen in the case of copper complexes. See, consider the copper 2 system, Cu2 plus system. Cu2 plus means we have the electronic configuration of copper is 3d9 4s2. In the case of Cu2 plus, it is 2 electrons will be removed from the s orbital. So, it is 3d9 4s0. So, that is a d9 system, that is Cu2 plus is a d9 system, and the electronic configuration is, when in the octahedral crystal field, you have the electronic configuration T2G6 and Eg3. T2G6 means the T2G orbitals are completely filled. Eg3 means it is only it has got only 3 electrons, or there is an unsymmetrical arrangement in the Eg orbital. So, a symmetrical arrangement in the T2G orbital, unsymmetrical electronic arrangement in the Eg orbital, means it has 2 possibilities, that is dz square 2, dx square minus y square 1, or the 2 electrons can be occupied in the dx square minus y square, that is dx square minus y square 2 and dz square 1. So, there are 2 possibilities. This is the case. Since see the case, that is it is a D9 system, that is we are discussing about copper 2 plus Cu2 plus system, means 9 electrons are there, that is we have in the first case, that is D2G and Eg, means for 6 electrons in the T2G and 3 electrons in the Eg. Now, there are 2 possibilities, that the third electron can occupy either dx square minus y square or dz square. The first situation is like this. If it is occupying the dz square orbital, means the third electron is moving to the dz square orbital, that dz square orbital, the arrangement will be like this. See this, the T2G orbitals in the tetragonal, we have 2 types of elongations, 2 types of tetragonal complexes, that is tetragonal elongation and tetragonal compression. If we are discussing about the tetragonal elongation, means the z orbitals are being pulled out from the metal, from the other, it is the two metal ligand bonds are different from other 4, or the two metal ligand bond lengths are greater than other 4 metal ligand bond length, that is elongation, tetragonal elongation. And when it is tetragonally elongated, what will happen? The z axis, the orbitals lying along the z axis will be having a lower repulsion, or the energy will be decreased in the case of the d orbitals lying along the z axis. Means, which are the d orbitals which are connected to the z axis, that is dxz, dyz and dz square. And so, we have the Jahn-Teller distortion like this, means dxz, dyz will be having a lower energy, followed by dxy. Here it was degenerate, but in the case of tetragonal elongation, these two are having a lower energy and this dxy is having a higher energy. When we are coming to the Eg orbitals, we have two Eg orbitals, dz square and dx square minus y square, and among these dz square is having a z component, and that will be having a lower energy because it is tetragonally elongated complex, means it is having a lower energy and dx square minus y square. And so, this is the tetragonal elongation, and now electrons are being filled up like this. We have D9 system. So, after 6 electron in the T2G, 7th will be moving, 8th here and 9th will be occupying the dz square. Why? Because dz square is having a lower energy. This is also called as Z out distortion. So, tetragonal elongation is also called as Z out distortion. And now, we are discussing about the tetragonal compression. Means the the orbitals which are along the z axis are being compressed like this, and when it is compressed, what will happen? The orbitals which are having the z component will be having the higher energy. So, the situation is like this, that is just reverse of that, that is dx y will be having a lower energy, dxz, dyz with higher energy, and here dx square minus y square will be having lower energy and dz square with higher energy. When electrons are being filled, it is like this, that is after 6 electrons in the T2G, 7th will be in the dx square minus y square, 8th in the dz square, 9th will be occupying the lower energy dx square minus y square. And so, this the tetragonal compression is also called as Z in distortion. So, we have two types of distortion, Z out and Z in distortion. So, in this case, if the copper Cu2 plus complex, since we have already seen that D9 system is having a strong Jahn-Teller distortion, it may be either Z out or Z in distortion. If it is Z out, the electron, the last electron will be occupying the dz square orbital of or if it is Z in distortion, the last electron, the 9th electron will be occupying the dx square minus y square orbital. And now, there are different factors that affect the crystal field splitting. The factors will be it can be numbered 1, 2, 3 up to 4 or 5 factors are there. First one is the oxidation state of the central metal atom. The first factor that affect the crystal field splitting is oxidation state of the central metal atom. We have in the coordination complexes, there is a central metal atom. That atom, central metal atom, will be having different oxidation state, and if the oxidation state, it was seen that if the oxidation state of the central metal atom is greater, crystal field stabilization energy is greater or splitting will be more. That is, if a complex ion is having a 2 plus oxidation state and a 3 plus oxidation state, the 3 plus oxidation state will be having a greater CFSE or crystal field splitting. We can conclude that as the oxidation state of the central metal atom increases, CFSE also increases. That is the first factor. Second is the nature of the central metal ion. Nature of the central metal ion means what is the type, what type of central metal ion is there. We know that this coordination complexes are formed by the transition metal ions, that is we have 3D 3D series, 4D series and 5D series. We have 3 type of transition metal ions, that is 3D, 4D and 5D series. When we are discussing, when we are investigating the CFSE of these three series, that is 3D, 4D and 5D, it was seen that 5D series is showing a greater crystal field splitting when compared to 4D, and when we are comparing 3D and 4D, it is 4D having a greater crystal field splitting. So, it can be concluded that 3D is having very much less crystal field splitting, followed by 4D, then 5D. That is, 5D series is having a greater CFSE. And now the third factor is the geometry of ligands. Geometry means the main geometry which we are studying are tetrahedral and octahedral complexes. When we compare these two complexes, we have seen that delta T is very much less than delta O. We have seen the the relationship between delta T and delta O. So, delta O will be having a greater splitting, and we have discussed what are the reasons for the difference in delta O and delta T, because the number of ligands is less in the case of delta T, and also there is no direct interaction in the case of delta T, in the case of tetrahedral complexes, that is why delta T is always less than delta O. Now, another factor is the nature of ligands. We have different types of ligands studied, that is weak field ligands, strong field ligands, etc. was discussed in the earlier classes. And these since there are different types of ligands, there is an arrangement of the ligands based on the increasing order of their splitting ability, that is crystal field splitting ability. Different ligands have different nature of splitting. We have seen that weak field ligands are they are not much capable of splitting, and strong field ligands are very much capable of splitting. So, we have arranged the increasing arrangement of ligands in the increasing order of their splitting ability. That is called as spectrochemical series, which is very important. Spectrochemical series is the arrangement of ligands based on the increasing order of their splitting ability. And here you can see the order, see this order. When we see the spectrochemical series, you can find that iodine I minus is having the lowest crystal field splitting ability, and the greatest is for Cn minus, which is equally having the ability with the CO and Cn minus is having the same ability, that is highest crystal field splitting ability. From I minus to CO minus, you can see that different ligands are arranged: I minus, Br minus, SCN minus, Cl minus, S2 minus, N3 minus, etc., etc. And just see the spectrochemical series. From there you can see that from I minus to H2O ligand, means water, H2O aqua complex. We have seen the different aqua complexes where H2O is acting as the ligand. In those cases means I minus to H2O, these ligands are called as weak field ligands, because they are having a lesser capacity or capability for splitting. From H2O means H2O and NCS as having a similar splitting ability, and from there to the CO, they are generally called as strong field ligands, because they are having a strong ability to split the d orbitals. So, when these weak field ligands are there present in the complex, the splitting of d orbitals will be very much less, and when the strong field ligands, for example, if it is a CO ligand or Cn minus ligand, such complexes will be having a high crystal field splitting. And that is all about the spectrochemical series. What is the spectrochemical series? It is the arrangement of ligands based on their ability to split. So, arrangement of the ligands based on their increasing order of their splitting ability. So, in this class we have discussed about the John-Teller distortion or tetragonal distortion, John-Teller theorem, which all complexes are undergoing strong John-Teller distortion, and what are the different reasons for that. We have seen particularly for the CO2 plus Cu2 plus system, that is D9 system. In the D9 system, there is an unsymmetrical electronic arrangement in the Eg orbital, and when there is an unsymmetrical electronic arrangement, there will be a when there is an unsymmetrical electronic arrangement in the Eg orbital, there will be a strong distortion, that is strong John-Teller distortion. And different factors that affect the crystal field splitting, different factors were discussed, and we have discussed the spectrochemical series. We have seen the spectrochemical series, which is very important. And now we are concluding this module. In the next module, we will be discussing, we will be continuing the theories of coordination compounds, that is we will be discussing about the final advanced theory, that is molecular orbital theory in coordination compound. And now thanks for watching this video. Thank you.